Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is the universe, from beginning to end. With me here in the studio to discuss this topic is our own Dr. Timothy Day. Timothy, welcome back to the guest side of the studio.
Thank you, Don. It's a pleasure to be here, no matter what side I'm sitting on.
Well, the universe, a big topic. No pun intended. Best place to start, I guess, would be in the beginning.
At the beginning. So we often wonder, how did the universe expand? How did it begin even? And there's been a lot of philosophical thought about it. I mean, as far as back as the Greeks and wondering the shape of the Earth, much less the shape of what a galaxy is and how many galaxies are there, and so on and so forth. And as we've moved into the 19th and 20th century, and our instruments have gotten bigger, more precise, able to see out farther, we learn to think in terms of not just different stars besides ours, but in fact that there are actually other galaxies besides our own galaxy. And that was done by a gentleman named Edwin Hubble around the 1900s. And he was actually able to measure how fast something was speeding away from our galaxy versus how fast something was coming towards us. And he could do that because the light would have either a red hue to it, which is a form of shift, meaning I'm going farther away from you, or he could find some galaxies that were doing a blue color shift, and that was the clue that, hey, I'm getting closer to you.
The Doppler effect.
The Doppler effect, exactly. Only in this case, not sound, but photons, light waves, changing and shifting. And that gave us a huge amount of information about how our galaxy might have really started. So there was this great theory up to this time that the universe was kind of a steady state. It was in constant recreation, but it didn't really change size very much. It didn't get a whole lot bigger. It didn't get a whole lot smaller. It was like it was a fountain, and it just kept generating more of itself and itself and itself like that.
So basically it was, is, and will be, according to that statement, it was always just there and will always be just like that. There won't be any vast change.
Yes. And so they called that the steady state model. Things didn't change much. There wasn't any great expansion or any great contraction. It just was this void that just kept getting filled up at the same pace that things might die off. And then one day somebody had this shocking idea that perhaps the universe started out from a Big Bang, that there was a point backwards in time where there was something that was like a black hole, infinitely dense and infinitely hot, and it managed to explode.
Such as in the image that we have right here.
Right at the very beginning of this image, you can see that white light to the left, and that represents the explosion, the primordial seed from the Big Bang from which everything came from. Big Bang, by the way, was a term of derision. It was originally meant to make fun of the astronomers who believed that this might be possible.
Starting all matter at a finite point.
At a finite point.
Moving out into this expanding universe.
One of the consequences of this is that if something explodes into space, well, then you should be able to run it backwards to the point at which it started. And that would give you the age of the universe so far. And so we began to look for that. What evidence do we have as we look deeper and harder and with more instrumentation. And what we began to see is evidence that, hey, this really might have happened this way.
So here we are looking out into the vast cosmos.
We are. So we're the person in yellow, and we're standing on the planet Earth, and there's little images for our solar system, Saturn and Jupiter and Mars. And then if we keep looking, we see galaxies or more parts of our own galaxy than distant galaxies, going back, even farther. We get to this point about 370,000 years ago where there's a sort of an optical wall. We can't see past that wall because that's the point at which the universe first became transparent. There was a point before that, back to the beginning of time, where it was so hot that light was not free to move through space. It was kind of a mystery. And so if you look at this image here, you can see, once again, the Big Bang on the left, and then you see that it expands very, very quickly. That's this plate that's on the left side just to the right of the Big Bang. And that's the cosmic microwave background. And you can see that there's a period of dark ages during that time. And then first stars start to form, and that's the blue.
So those first stars would actually be that 380 million year threshold from the beginning, that beyond which, at this point in time, we can't look back beyond.
That's right.
Okay.
We can't see past that point in time. Right.
And we're sitting out here now about 13.8 billion years from the beginning.
Yep.
And then trying to look back and some of the things that we can see.
And we have special probes that can see back about that far, 380,000 years, and then no more. That's the wall that keeps us blinded to see what's happened in the very earliest states of the universe. So at first we thought it was all the same temperature, all perfectly just homogeneous. The more we looked, the more we began to see that the microwave background actually had some patterning to it. You could see some denser places and some cooler places. Here's a great example of that.
Yes, this is a great example of that.
So getting to this point, the very first pictures of the microwave background, they were so insensitive, even although the instruments were sensitive, they were so insensitive that they really couldn't see any differences. They just knew that there was a time at which everything seemed to stop. Our best images now from better satellites show you that there are hot points and cool points, and those represent areas where matter has clumped and heat has clumped, and then the blue areas are places where there are voids and there's no heat and there's very little matter.
So there's that unevenness.
So we get that unevenness. So here's one more example that the universe is almost perfectly homogeneous, but if you look hard enough, you find some patches, some unevenness here and there.
So we've seen the beginning and this early expansion as it expands out past the dark ages to the beginning of stars. Then we have billions of years that we move along. Is there still a rapid expansion of the universe, or is something else happening?
The rapid expansion of the universe takes place very early, and what it does, very early after the Big Bang, and what it does is it accounts for a whole bunch of things. So if we look at a slide of inflation in the smooth universe, okay, we can see that inflationary period actually took just a few minutes of time, or even seconds, and then the inflation period is over. And at first, inflation was like, give me a break. Nobody really took it seriously. Why this? Why now? And then with further examination, we began to see that it took care of a whole bunch of problems. It took care of why things were particularly homogeneous, very much the same in all directions, why the size of the universe seemed to be the same no matter where you were, and a number of other features that have become interesting to think about. So while we don't know, once again, the cause of inflation, what we do see is that, hey, that's a seemingly crazy idea that is actually accounting for a good deal of what we observe very nicely.
And so this early expansion seems to have slowed down a bit over the intervening billion years or several billion years.
Yes. The first expansion, the inflationary expansion, was extremely quick. Started almost right away after the Big Bang and ended before we even got to the 1 second mark in our own universe. Okay, and then there was a dark space matter, and then there was some additional expansion, but at a much slower rate now. One that we sort of have become used to, and in fact, it went to about 7 or 8 billion years.
And we assumed that until recently that slowed expansion was still going on.
We did.
Okay. But it seems that in the last few decades, maybe a little bit longer since Edwin Hubble in the 20s, we have found that that's not necessarily the case.
There's more to the story.
Which I think we'll take care of in the second part of the program here. We'll stop for a moment, let you assimilate all of this information. We'll take a quick break. If you have a question, please send us an email. As always, you can send it to the address that you see down there at the bottom of your screen. And coming up next is Term of the Month with Stephen Whitty. And once he's finished, we'll be back to talk about the speed up of our universe. So don't go away.
The term of the month really isn't a term. It's the determination of the age of the universe. There are 3 ways that we have done this. The age of the oldest stars that we can see. The newest technique for aging stars is gyrochronology. And it seems to be about, give you estimates within 15% of whatever is correct. And then we have the expansion rate of the universe. That's the Hubble constant. And we've been trying to measure this, and we've gotten better and better over decades. And then finally, the cosmic microwave background radiation, using the lambda CDM concordance model and data from the satellites WMAP and the more recent Planck satellite, we have come up with a value of 13.799 billion years, plus or minus 21 million years. It's actually very, very good. These have converged in the last 5 to 10 years, and they now agree with each other. And that is Term of the Month, determination of the age of the universe.
Thanks, Steve, and welcome back to the program. The topic is the universe and its expansion. With me is our own Dr. Timothy Day. And in the first part, we talked about the initial expansion and then the slowdown, which we thought was continuing just the way it always had. But apparently, we have new information that tells us that that's not the case.
Well, let's go to a slide that shows us the fact that inflation gave us a smooth, cool universe after the Big Bang took place. So here we have a slide that shows the fact that the theorists are looking at everything and going, wait, it all seems to be evenly distributed. It doesn't matter where you're looking from. The same stuff is off to your left as to your right, or you're up or you're down. It's all relative, of course, to where you are. But everybody's kind of scratching their heads and they're saying, well, shouldn't there be more stuff to the left or to the right or whatever else? And we just had the hardest time getting a grip on that. Why is it doing that? Why is it being so even? It's almost as if it's a cue ball or an 8-ball. You get this inflation, just like the 8-ball to the Earth. It's that sameness that space-time's curvature has, and it expands everywhere. Everywhere you look, you get the same smoothness. And we're going, what caused inflation? What happened that the universe formed in this way?
And now we have the problem, quote unquote, of the speed up. What's causing it? What thing is putting its foot on the accelerator pedal, so to speak?
Two things happened that just surprised the heck out of us. And when I say us, I mean, astroastronomers who study the fate of the universe. There is, the first one was that as we looked at the mass of our entire galaxy, all of the lit up arms and little points of mass, globular clusters, top and bottom, and we measure the speed with which our galaxy is going around, or other galaxies are going around, the Andromeda, we can measure quite a few. We would do the best guess about how much mass, and then how much mass needs to be there in order to keep it all from flying apart. And we expected to find, well, there's enough mass because it's not all flying apart.
So what we see is what we have, and that holds it all together.
Well, that's what we thought. In turn, it happens that you have to have something else. There's got to be some sort of matter. And the matter will determine whether we have a flat universe or whether we have an open universe or a closed universe. We thought that those fates depended entirely on the matter we could see, and then we learned that there's an awful lot of matter that we can't see, except for the fact we know it's there because we could feel it. It has mass. It keeps the galaxies from flying apart. And we were just amazed by this discovery. And so we didn't know what to call it, so we called it dark matter. So that was the first of two discoveries. And the next was that we got a sort of a kickstart in the speed which we're expanding. And so you can see on this slide here that during inflation, the universe expanded much faster than the speed of light. That was the very early inflation. Boy, it has a lot of zeros in it, doesn't it? 35 zeros. 35 zeros is hard to wrap your mind around. This is a trillionth of a trillionth of a trillionth of a second after the Big Bang. And this inflation lasted another tiny fraction of a second. The number would have been about 32. So we once again we came out into a smooth, slowed down, expanding universe, and then what happens is we came to at about the 8 billion year old mark. We realized that nice, smooth slowing down actually started to increase in speed again. And that was, again, totally unexpected. And so what we did was see, hey, it's all starting to speed up again. So it's not just about measuring all the dark mass, which we figured out to be something like 25% of our total universe's mass. Even if we couldn't see it, we could see the pole. So what we did next was realize that there's some energy out there that is now beginning to take hold of things, including dark matter, and pushing it out.
Such as in the slide we have here, the accelerating expansion.
If you follow the slide along the top, you'll see slowing expansion, and then all of a sudden there's a point at about 8 billion years where the expansion really starts to pick up speed. A little bit at first, but now we're at 13.7 billion years, and we're just seeing it get faster and faster and faster. Same way we saw change in speed from the Hubble constant, we're seeing that same change in speed from the universe as a whole. Again, confuse scientists, confuse physicists, and so what they do is call it dark matter. And what it is, we haven't a clue. If for young people going into this field for the first time, it's really an exciting time because there's a lot to learn. There's a lot to bring into your awareness, into your consciousness, and say, what have we discovered, and what's still waiting out there?
Well, with this in mind, it brings up, I guess, the question. It's expanding. What does this acceleration mean going forward into the future, trillions of years from now?
Exactly. We're not sure. We just don't know. We think that if everything remained just as it is now, that our universe would just keep expanding, and eventually it would freeze, essentially. Things would begin to cool off so much that stars would die out into cinders, and the cinders would cool, and black holes would actually evaporate away, and we would come to have a universe where there's not even things like neutrons or protons anymore. There's just the particles that make them up, and electrons and neutrinos, things called leptons as a class, and they get farther and farther apart, and the universe gets redder and redder, and finally it slows down and becomes very, very flat. And it becomes slow and red, and that's about it. Just above absolute zero.
Again, going back to our flat universe model right there in the slide. It almost seems like everything will just die out, and you wonder, will there be anything left to perhaps draw it all back to the beginning?
To the beginning
Or
again.
will it just dissipate away and
that's where we're left hanging right now in terms of theoretical physics. Now, I would say, well, this is probably the future, but we've had so many astonishing changes in just the last 50 years that who knows what can happen? What's going to pop up on the plate for dinner next?
Exactly.
We've just got this surprising bevy.
I mean, we have this dateline of events that we can see here quickly in our last minute. So it really does make you wonder, like I say, what's happened in just our lifetimes, and in the next 100 years, will we figure out what it is and then be able to figure out how the universe might evolve itself? Well, I do want to take time now to thank our guest, Dr. Tim Day, member of the Ford Club, for talking about this, I think, a fascinating topic. You can check our club website for other information and interesting topics. But before we go to Stephen with What's Up in the Night Sky, I do want to mention again that coming up on Friday, September 9th and Saturday, September 10th, is Astronomy at the Beach, being held at Kensington Metro Park out near Brighton, Michigan. It's one of the largest public star parties in the Midwest. We encourage you to attend. To find more information, the easiest way is just Google the Astronomy at the Beach name, Astronomy at the Beach, and it'll take you right to the first listing, which is the Kensington Metro Park website. You can get all the information there. We encourage you to attend. I believe this is the 20th year now. It's a great event, great for families, kids, students. We hope to see you there. So with that, we turn it over to Stephen, and thanks for watching.
Thanks, Don. What's up in the night sky for August 2016? The days are getting longer, so sunrise goes from maybe 6:30 to 7, and sunset goes from almost 9 p.m. to 8 p.m., so later in the morning by 30 minutes and earlier in the evening by 40 minutes. Days are getting shorter. The month starts on the 2nd with a new moon. On the 10th, we have the first quarter moon. On the 18th, we have a full moon. And on the 24th, we have the third quarter moon. Mercury and Venus, here shown on the 1st of August at 9 p.m. Mercury, it turns out to be better earlier in the month, and Venus gets higher in the sky later in the month. So later is better for Venus, and earlier in the month is better for Mercury. For Mars and Saturn, they're going to be visible all month long. They set roughly after midnight. So here shown in the middle of the month at 10 p.m., that's a decent time of night to look. Jupiter, here shown on the 1st, is, I think, better earlier in the month. It has superior conjunction on the 26th of September, which means it goes behind the Sun pretty soon, next month. Here shown on August 15th at 11 p.m., we have Pluto and Neptune. So Pluto on the right. We happen to have a nearly full moon near Pluto, so that's not probably the best day of the month, but almost any time of the month, this is a great time to look at Pluto if you're going to look at it. You need a 10-inch telescope, and you need a much better finder chart than this one. Maybe an observatory locally has those things. You can take a look. The Perseid meteor shower peaks on the 12th of August. There's an outburst that seems likely, 150 to 200 meteors per hour, up from the normal 80 per hour. The particles from Comet Swift-Tuttle give us the meteors. So the Perseid meteor shower is quite broad, and you can see Perseid meteors anywhere from July 17th in the past already and to August 24th. So before the 12th is better because the moon isn't as bright. Dress warm, look at the full sky, streaks that go back to Perseus, that's where they come from, are Perseids. And that's what's up in the night sky for August 2016. Keep looking up in the night sky. It's the greatest free show over your head every single night.